I want to talk about like Darren said, an absolute classic of a paper, Error Detecting and Error Correcting Codes by Richard Hamming. Really, his nickname was Dick, and I was wondering if I should refer to him as Dick Hamming during this presentation, but I decided against it, so we're just going to be Hamming for the rest of this presentation. This paper is great for a few reasons. The techniques that it talks about are still like in use in most of the computers they use every day. If you ever used error correcting memories or ECC RAM, you're probably, the way that the information was moved from the actual like RAM sticks or the actual rest of the computer was probably done using some form of error correcting codes. But the thing that I really love about this thing is that it is a bombshell of a time capsule. It does a really good job, I think, of describing in the way that we thought about computing, about technology, about science, all the way in 1950. It was also written in like a very exciting time, which I'll talk a little bit about what was happening right at the end of the 1940s, beginning of the 1950s at Bell Labs. It's a cool paper. I'm going to commit kind of like a sin, which is I'm just going to read from the paper for a bit. I'm going to read the first 3 paragraphs. And I'm going to read the first 3 paragraphs because they don't involve any of the actual like math or techniques, but they set the tone so well. It's like, a really good like introduction to a book. It's like in a land far, far away. He starts by saying the author was led to the study given in this paper from a consideration of large-scale computing machines in which a large number of operations must be performed without a single error in the end result. No errors. The problem of, quote, doing things right, end quote, on a large scale is not essentially new. They were doing things wrong before, but they're also doing things right. In a telephone central office, for example, a very large number of operations are performed while the errors leading to wrong numbers are kept well under control, though they have not been completely eliminated. This has been achieved in part through the use of self-checking circuits. The occasional failures that escape routine checking is still detected by the customer and will, if it persists, result in customer complaint. Well, if it is transient, it will produce only occasional wrong numbers. At the same time, the rest of the central office functions satisfactorily. So his idea is like, if there's an error and you're trying to like call someone and you don't get to them, you'll just hear the wrong person and like you'll know really quickly. Like the correction for like calling people is like somebody being like, no, I have no idea who you are, which I feel like we've all experienced. In a digital computer, on the other hand, a single failure usually means the complete failure in the sense that if it is detected, no more computing can be done until the feature is located and corrected. Well, if it escapes detection, then it invalidates all subsequent operations of the machine. Put in other words, in a telephone central office, there are a number of parallel paths which are more or less independent of each other. In a digital machine, there's usually a single long path which passes through the same piece of equipment many, many times before the answer is obtained. The idea here is, right, like this is, I think, more subtle than it might seem, right? They were just thinking about telephones back then, right? Like this is like Bell Laboratories, right? The idea is you just call someone, they pick up, and then you talk to them, and the circuit's kind of like established. The idea that you have a machine, it kind of like repeats onto itself in a way that's almost like recursive, right? Like he's, in a way, kind of like spiritually describing recursion here, and is talking about how at any point during this kind of like recursive operation, like things shouldn't fail. Second paragraph. In transmitting information from one place to another, digital machines use codes, which are simply sets of symbols to which meanings or values are attached. Examples of codes which were designed to detect isolated errors are numerous. Among them are the highly developed 2 out of 5 codes and 3 out of 7 codes. In some situations, self-checking is not enough. For example, in the Model 5 relay computers built by Bell Telephone Laboratories for the Aberdeen Proving Grounds, observations in the early period indicated about 2 or 3 relay failures per day in the 8,900 relays. It's a good number, 8,900 relays. 8,900 relays, if you think about the number of transistors in your CPU, it's going to compare those two things. Of the 2 computers, representing about 1 failure per 2 to 3 million relay operations. Every time a relay switch, every 2 to 3 million of those, one of those goes kaput. The self-checking feature meant that these failures did not introduce undetected errors. Since the machines were run on an unattended basis over nights and weekends, however, the errors meant that frequently the computation came to a halt, although often the machines took up new problems. The present trend is towards electronic speeds in digital computers, where the basic elements are somewhat more reliable per operation than relays. However, the incidence of isolated failures, even when detected, may seriously interfere with the normal use of such machines. Thus, it appears desirable to examine the next steps beyond error detection, namely error correction. This has everything. This is amazing, right? Like, it like seems so like matter of fact because this is what he was thinking about. But he's talking about like the culture at Bell Labs. Like, yeah, we're doing like technology or research, but really what we're here is to like make phones work better. And all of this is about like how can I make phones work better? I love the bit about like customers And the sense about like digital speed is like, we used to do things with things kind of like flipping back and forth mechanically, like, but digital speed is coming. What is digital speed? We'll talk about that. Also, he talked about relays. Remember those? I'll talk about those in a second. This is our author. This is our good friend Hemming, nickname redacted. He was born in Chicago in 1915. Hemming initially wanted to study engineering, but the Depression hit his family kind of hard, and the only place they could send him was University of Chicago, where he got a scholarship. U Chicago didn't have an engineering department then. They still don't, I think. If somebody knows, correct me. So he ended up auspiciously studying mathematics. He got a PhD at the University of Illinois in 1942 and spent 3 years teaching before, in 1945, he was recruited to join the Manhattan Project, which I think after Oppenheimer last year, we're all kind of like familiar with. This is what he did at the Manhattan Project. He described himself as a computer janitor, which is a cool term, a computer janitor. The idea is that they had all of these kind of like, notable physicists that, we based in movies. This is Ede or Edward Teller. And, of course, we all know about Oppenheimer. They were kind of like doing the serious work. And he was sitting there, and all he had to do was like sit in this room and run computations. He found this to be a very kind of like unsatisfactory job. In later kind of like lectures, he talked about how he would look with envy at all these great physicists doing great work. There's one quote I want to share, and I feel like I've been quoting a lot. Most of this is not going to be quotes. I'm mostly done with quotes, but it's just like also like awesome. And he said, this is a later lecture, shortly before the first field test, a man asked me to check some arithmetic he had done. And I agreed, thinking to fob it off on some subordinate. When I asked what it was, he said, it is the probability that the test bomb will ignite the whole atmosphere. So he's like sitting here and he's kind of running these calculations. He's like, what's this for? And it's like, it's a chance we all die. I decided I would check it myself. The next day when he came for the answers, I remarked to him, the arithmetic was apparently correct, but I do not know about the formulas for the capture cross-sections of oxygen and nitrogen. After all, there could be no experiment at the needed energy levels. He replied like a physicist talking to a mathematician, which is understated, and that he wanted me to check the arithmetic, not the physics, and left. I said to myself, what have you done, Hemming? You are involved in risking all of life that is known in the universe, and you do not know how much of an essential part. I was pacing up and down the corridor when a friend asked me what was bothering me. I told him, his reply was, never mind, Hemming, no one will ever blame you. I couldn't find it confirmed, but I think the person he was running the calculations for was Teller Ede, or Edward Teller, also played by Benny Safdie in the Oppenheimer movie, kind of like seen here in that notable scene. Very Hungarian man. I don't know. I can explain what that means, I guess, after the talk. After finishing the Manhattan Project, in 1946, he left for Bell Labs. And he left for Bell Labs with, articulated, kind of like self-determination of doing something great. So he was really interested in doing great work. Bell Labs was an incredible place at that time, right? Like this was the hub where a lot of the technology and innovation that kind of like powers the modern world was kind of like cradled. It was, however, supported by AT&T being a kind of like de facto regulated monopoly. Everything that they did, and you can get that from the paper, was in support of the system being the system of telecommunication that spans the entire United States. Bell Labs was originally located in a building you can still see from the West Side Highway. So you can kind of like go around and you can see it. It's, I think, in Greenwich Village. This is a picture of the Murray Hill headquarters. And, this modern picture, you can see the cars. The design of the building is kind of cool because it kind of like epitomizes the philosophy of the place. It's got this really kind of like long hallway in the middle. And the idea was like people are going to have to like walk across the hallway and kind of like bump into each other. The idea was even if people are working on two very separate problems, they might like bump into each other, start talking like everybody here, and maybe realize that there's some commonality between some of the problems that they were working on. The kind of like design of the place was intended to kind of foster as much, quote unquote collaboration as they could. Bill Gates at some point said that if he could go back to any moment in time, he'd go back to Bell Labs in December of 1947. I'll talk about what happened there in just a moment. But a bit on what Hemming did at Bell Labs. So Bell Labs employed mathematicians as a kind of consultants. They were there to kind of help add rigor and kind of help think through mathematical problems that physicists and chemists and engineers were working on. So the idea is they're kind of like consultants. They come in and they kind of get attached to a project and like they do their math because nobody wants to like sit there and like do calculus and like, integrate functions. And then, everybody can like go on with their day and like do cool stuff like, purify like silicon or, whatever the heck they were doing. There are a bunch of like important mathematicians at that time. There was one guy, Claude Shannon, who's a name I hope you all recognize. If not, I'll highlight in a second, that Hemming actually shared an office with So he at some point was sitting next to Shannon, which, I think, kind of bleeds into this paper. The other thing I want to talk about is what computing was like at that point in time. So, I talked about like 1947, and the thing that happened in December of 1947 is the first proof of transistors working, and I'll have a picture of that later. But computers at that time were still electromechanical; they're still based on relays, and this is a picture of a relay. It's from the original patent filed by Samuel Morse for the telegraph. So this is where kind of relays invented. The idea is you got this coil right here, and if you run a current through the coil, it kind of like pushes something, creates a mechanical action. And what you can do is you can basically use that as a way to basically simulate various types of like circuits. Those relays, as we talked about, kind of like failed a lot. Another like piece of like computer history is the word bug we all know comes from a moth that ended up in a computer, so they called it a bug. That moth apparently ended up inside the relay, I think inside the actual like, coil itself, and just prevented the actual like moving part from like connecting. The computer that Hemming was working on, this picture right here, it's the Bell 5 computer. They're all kind of like one of one, right? Like they didn't like reproduce computers. The idea of like, mass manufacturing computers just wasn't feasible yet. So they made all individual computers, which all had individual names. And here you see the Bell 5, which, as we learned earlier, had about 8,900 relays. Super expensive machine, broke a lot, super unreliable. The kind of like problem that Hemming was facing is that he wanted to just run calculations overnight. I think we all at some point just like ran a query that would last for like a few minutes and just kind of waited for it to come back. He wanted to do that with some calculations he ran all weekend. But at some point there'd be an error. It would stop and come back on Monday and say various expletives. This was kind of the problem that was motivating him. The other kind of like way that computers worked, and I want to mention this just because it's cool, are using vacuum tubes. Who here is familiar with vacuum tubes? I didn't study electrical engineering, so I just know them from my friends who like have like cool like guitar amplifiers. But they work in very similar ways. You have kind of like a filament, and you have a plate, and then you have this grid in the middle. And if you run a current through the grid, you're basically able to kind of like accelerate electrons from the filament to the plate. So they act as a really useful amplifiers, and this is kind of where they were originally deployed at Bell Labs. But you can also imagine how you can use them to also kind of have these three prongs and simulate various circuits. And we also see a vacuum tube-based computer here. This is the ENIAC in Philadelphia. It was built right after World War II, I want to say. And similarly, just to get a sense of like the error rates here, I lost my place. Several tubes burn out almost every day, leaving ENIAC non-functional about half the time. Special high reliability tubes were not available until 1948. Most of these failures, however, occurred during warm-up and cool-down periods when the tube heaters and cathodes were under the most thermal stress. Engineers reduced ENIAC tube failures to the more acceptable rate of 1 tube every 2 days, which is remarkable, right, to like think about it. According to an interview in 1989 with Eckert, we had a tube fail about every 2 days, and we could locate the problem within 15 minutes. So imagine like something's not working, and you got it down to a science, so you only had to spend 15 minutes finding the tube that burned down. In 1954, the longest continuous period of operation without a failure was 116 hours, close to 5 days. So the longest you can keep one of these machines running was 5 days, and then just something would happen, it would burn out. Also, these things were super like energy hungry. There's like some anecdotes that whenever the ENIAC was running, like it was consuming so much power in Philadelphia that the lights would kind of like dim. So you can kind of tell, like in like Stranger Things, the lights kind of dim, where like there's like demons around, like and you can tell that they powered on the computer. There are two really kind of like important discoveries, inventions, theories. You can define them whichever way you want, and we'll talk about it at the end, but that happened at Bell Labs right around this time. The two I want to highlight are first, the first demonstration of a successful transistor, and the other one is the publication of Claude Shannon's A Mathematical Theory of Communication. And I think those two kind of like developments like really set the stage for this paper. The first transistor experiment used a piece of germanium. Germanium, I don't know how you say it, either or. This is kind of like the bottom thing you see at the bottom there. And then they had these kind of like gold plates and then run a current through the germanium, and it was able to amplify the current that was running through these two gold plates that were inserted on top of this kind of like plastic piece in the middle. This was like remarkable, right? Like it would still be about 3-4 years before they were able to do this with silicon, but like the idea that you could like create these devices that use solid state materials as opposed to having to use these expensive like relays or vacuum tubes was revolutionary, and they knew it immediately. The kind of like other big kind of like idea is Claude Shannon's paper, and I think Claude Shannon is one of those names that like everybody who works in this industry should know. His master's thesis described how you could use electrical circuits to define Boolean logic. So if you ever seen kind of like AND and OR gates, like defining like various like adders, and this is all from Claude Shannon's like fucking master's thesis. Remarkable. Really funny guy regardless, a lot of other cool stuff he did. But the notable one that made him famous is the publication of this paper in 1948 that defined information using this idea of entropy, right? Like you get some new information, like how surprising is it? And then you can use that kind of like level of surprisingness to encode different messages. That's about as much detail as I want to get into. There's actually a PapersWeLove presentation on this paper that's very good, I think from the SF meetup. You can look it up afterwards. This is one of the theorems from Shannon's paper. Let a discrete channel have the capacity C and a discrete source, the entropy per second H. So you have a capacity and then you have how much information you can kind of put through it. If the entropy is less than the capacity, there exists a coding system such that the output of the source can be transmitted over the channel with an arbitrarily small frequency of errors. What basically Shannon is able to prove here is that if we have some source of information, we're able to add some redundancy to it. And we can add as much redundancy as we want in order to reduce the amount of errors that happen during transmission. He didn't tell you how to do that. He just told you it was possible. And basically his whole thing was like, let's somebody else figure out how to like define one of these schemes. So we know we can add redundancy in order to be able to kind of reduce errors. We also know that working with computers sucks. It's miserable. And those are kind of like the two kind of currents that are going on as Hemming is publishing his paper. So this paper comes out and Hemming starts with just a very simple method for constructing codes. And it works as follows. He kind of like starts by thinking about the existing codes that exist. So these are 2.5 codes. They're still used for barcode, I think. They're using for like transmitting numbers. The idea is you could encode all 10 digits in such a way that every 5 bits would have 2 ones and 3 zeros. So if you got 2 ones and 3 zeros, you got a correct message. If not, you have to do something to figure out where things went wrong. The other method is repetition. And this is like the dumbest one, but I think sometimes starting from like, the simple way of doing things, brute force, if you will, is kind of a way to like lead to, better ways to refine it. And it's just, you just repeat the message. If you want to send 110011, you just send it twice. And, if there's an error in there, you send it, 3 times, and then you can kind of like create some consensus there. It's dumb, but it works. Just super, super inefficient. The last method, and this is kind of where we start, is the idea of parity. So let's say you have 7 bits of information. You have a message that's 7 bits. And you want to find out if the message is correct or not. What you do is you add either a 1 or 0 at the end to make the number of ones even, to give it an even parity. So if the message is just a string of 6 ones, you add 1 at the end. Ooh, I calculated these wrong. They should be flipped. It should be 0 and it should be 1, but forgive me. Likewise, if you get yourself 4 ones, I didn't get it wrong. I got the bottom one wrong, I got the top one. You get the top one wrong, the bottom one right, but I hope the idea makes sense. Remember this idea of parity, because this is kind of like what underpins this construction. Then he kind of like describes the process here, right? I'm not going to read this out loud. You can see this will be in the slides. But there's kind of like 3 constants we can play with here, and these constants are important because they help us reason about kind of like the class of codes. You have some message of size n, so you have n bits. Then you have some number k. This is the amount of bits you use to do some sort of checking. And then you have m, which is the message, the actual like payload you can have in there. So you have m, is equal to n minus k. This is kind of like intuitive, right? Like if you have like 8 bits, you use 4 of those bits to kind of like do some sort of error checking. You have 4 bits left. 2 to the 4 is how many different symbols you can kind of like encode in there. This is all he's saying. It's a pretty straightforward idea. It's like pick your payload. How much of it is to check? How much of it is just actual information? The kind of like insight here, and the place where this gets really cool, is he thinks about where you might put these kind of like check bits. So if you have 4 for the message and you have 4 for checking, where do you put them? One option is you can kind of like put them in the end, but what he realizes is you can kind of put them at powers of 2. So if you have, a check at bit number 1, it can check positions 1, 3, 5, 7, 9, 11, etc. 2, 2, 3, 6, 7, 10, etc. And so forth and so on. Does anybody kind of like notice the pattern? Like, why is this useful? Does anybody have kind of intuition about why this works? Show me in a bit, it's cool. You kind of end up with this relationship here, but to kind of like demonstrate it, the final thing he does is add 1 bit for the whole message. So you have these kind of like check bits, and then you have 1 bit for the whole message. And that's all it does. And I have a demo for you, which I think is going to make this make a lot more sense. So here we have 16 bits. We have the 4 check bits right here that are marked like a little P right here. And then you have this 0th bit right here that can check the parity of the whole message. What he gives us is a way we might be able to kind of like construct this message, right? So what we can do, for example, if we have take 5 right here, we need to make sure that it has even parity with this parity check, and you need to make sure it has even parity with this parity check. Finally, the whole message needs to have even parity. So there's kind of like a construction process here. What you can notice pretty quickly is the reason why these bits work right here, the 1 bit and the 4 bit, is because if you kind of like look at like the number here, all the powers of 2 are going to have kind of like a clean just zeros with a number in a position. So, 4 has a 1 right here, 1 has a 1 right here, and 5 has a 1 in the second position and the fourth position. And you can kind of see how it highlights here, right? Like, if you go over any particular like parity bit, you can see which bits it's going to check. So this checks the whole message, but each one of these parity bits just check a particular kind of like subset of the message. And I'm just going to kind of repeat this for the sake of kind of like demonstrating it, right? Like, let's say you like take this bit, and let's also pick, what the heck? Let's pick this bit right here. What am I looking for? I'm looking for this one. You need to make sure it has even parity. Let's just pick this one. You need to make sure it has even parity in all these numbers, even parity in these numbers. This is not required because it's already at even parity. You need to have even parity here, and what we have is a well-formed message. Again, you can kind of repeat that all sorts of ways. So you go here, even parity, even parity. This is not even, so we got a ticket. This is not even, so we got a ticket, and we end up with a valid message. It's really fun. I don't know. It's kind of like fun to like mess with this. This method of construction, I'll also post this visualizations afterwards so everybody can like click around. The thing is, like, this message of construction also tells us how we might be able to like detect an error. So like, let's say that we untick this bit right here. All we have to do is find the places where there's no even parity, and that will tell us exactly the location of where our error has occurred. So if you go here, there's no even parity. There's no even parity. If we go here, there's no even parity. So we know it's going to be probably in this column, right? Because it's going to be in the intersection of these bits that we're checking and these bits that we're checking. So somewhere in this column, we're going to have an error. We can go right here. We have even parity. You can kind of tell. We can go right here. We don't have even parity. So because this works but this doesn't, it wouldn't be this column. So it would be the intersection of this row right here and this column. We take it. Found the error. It's really fun to kind of like mess with this, but it kind of hides the really kind of like powerful technique behind this. I'll tell you in a second, but can somebody tell what operation we're performing here? There's one bitwise operation we're performing that enables this whole thing. XOR. It's an XOR, and I'll show why in a second. But like, all we're doing is just XORing this message. What like even parity here means is that if you have two numbers and you XOR them together, you just end up with 0. The other thing we can kind of realize by messing with this is what happens if we have an error of 2. So if 2 bits kind of go astray. If we untick these 2 bits, we can use the same algorithm for kind of like finding the source of the error. But even if we find it, we take it right here, right? Like, we're not going to end up with an even parity across the whole message. Like, if 2 bits got flipped, the whole message is going to be wrong. And there's kind of like the intuition here of like, okay, like what happens if it's like, 2 bits, but it leads to another valid message, and that can't happen. And we'll show why in a second. But it's really cool, right? It's a really cool scheme. We can kind of like notice a few things about it. First of all, it's just an XOR, right? Like, all we have to do is basically XOR like all of the various kind of like bits together, and the result will tell us exactly where we're looking. Flip that bit. If it works, we find our error. If it didn't, something went wrong. This is super, super straightforward to like implement just using basic like XOR gates. This is like a schematic I found just like on the first page of like Google search results, which feels kind of hacky, but like, build it yourself, prove it. There's a lot of like videos online of people doing it, but like, it's very easy to take kind of like these 4 bits, add these kind of like check bits, and then like, undo the process. And you can see it here just in the schematic. The other thing is like, again, if 2 bits get flipped, we know something went wrong, but we're not sure where. And where is kind of like more of a subtle point than maybe we give it, credit for. Like where it means is like we don't really know where we started. We don't, if there's one bit that got flipped, we know exactly which code point to kind of like return to. But if if two bits got flipped, we don't really know where that came from. So, if we kind of flip one bit here, we do that. But if we flip, two bits here, we can flip this like 7. It's not going to work. The final thing to notice, right, is that this scheme scales really well when the total size of the message, n, we're talking about n, m, and k, when n goes up, like this scheme still works for finding single bit errors, right? So in the paper, Hemming describes it for messages that are kind of like 8 bits long. We just demonstrate for messages of 16 bits long. It's not hard to show how we can use the exact same scheme with the exact same parity bits to go 32, 64, 128 messages. It scales really well with n. It's not clear how it scales with k. So what do you mean scale with k, right? Like how will we be able to kind of like find out if there are like 2 errors, right? If there are 2 errors, how will we be able to find them? What's a general scheme for kind of being able to do that for like any arbitrary number of errors we want to correct? So taking this question, Hemming moves to the second part of the paper, and he talks about how can you reason about these codes a bit more broadly. And to do that, he develops a geometric model. And the geometric model uses what's called now a Hemming distance. It's always really funny because you read these papers and then they name the metric after the person. But like they'll never name it after. Oh, I invented the Hemming distance. My name is Hemming. It sounds ridiculous. But this is kind of what it would be called in like most textbooks that would refer to it. The idea of a Hemming distance is pretty straightforward, right? Like take 2 bit strings. The number of bits that are different between them is going to be your Hemming distance. So between 2 points, x and y, the distance is how many bits are different. And, it achieves these really nice properties insofar as it creates what's called a metric space. And a metric space is a category of like these different mathematical spaces where if you can show something as a metric space, you get a lot of like other stuff for free. You can do all sorts of other like cool math on it. I'll give an example of some math you can do in a second. The way you show it's a metric space is by proving kind of like these 3 properties. So if these 3 properties hold on your distance function, you get yourself a metric space. And it's that the distance between 2 points is 0. Pretty straightforward. 2 bit strings are the same. No bits are different. 0. It's only bigger than 0 if they're different, which again, it's one of those like mathematical instructions that's obvious, but you state it explicitly and it's important. And then it achieves the triangle inequality, which instead of just saying the word bit a lot, if you imagine a triangle, right, like you have A, B, and C, it should always be that the distance from A to C is less than or equal to the distance from AB plus B to C. So if you have the kind of like hypotenuse, its length should always be less than or equal to the lengths of the sides combined. And he gives an example here. It's nice. You can see it like, nice and straightforward. One of the nice things mathematically you can do with metric spaces is that you can define spheres. And spheres look very differently in different metric spaces. So in the Euclidean space that we all know and love, which is, this is how you did most of your kind of like high school, middle school, and probably college, like math is you work in the Euclidean space. A sphere is just that. It's like a circle, right? A sphere is defined as all points in the metric space that are an equal distance from the center. So that's the sphere. But you can do this in other metrics. So this is the taxicab metric. We're in Manhattan. This is, where kind of like the ideas for the taxicab metrics maybe were inculated. The taxicab metric defines distance as the number of cross sections you have to cross. So what we see here is a sphere of radius 2 in the taxicab metric. So all points here are a distance of 2 from that middle point. And it's pretty intuitive, right? You have to go 1 and 2 sections, and these would be all the points that are 2 sections apart from that middle point. Hemming's idea is like, what if we define spheres in this kind of like metric space using the Hemming distance? And to kind of help understand that, I created this visualization here. So this is the entire set of all possible points in the space described by a bit string of length 8. I laid them out just by using kind of like the last 4 binary digits or the first 4 binary digits. So the row here corresponds to those first 4. The row corresponds to, the column corresponds to the last 4. I'm messing up NDNS here. I hope nobody's mad at me. What we're going to do is we're going to take all the valid code points in the space, so all the code points that have no errors, we're going to kind of like enlarge them. So this is kind of what they're going to look like. So, we knew earlier that, if we have 8-bit string, we have 4 bits for information. We have 2 to the power of 4 different valid code points. That makes sense. Then what we're going to do is we're going to discolor all the code points that are a distance of 2. So this is all code points that had 2 errors. And you can discolor them, and this is kind of what it looks like. And the last thing we're going to do is we're going to showcase these spheres. Now the idea is, again, you can kind of like bit flip and it kind of like jumps all over this kind of like space right here. But we're going to visualize spheres by giving each sphere a distinct color. So this is kind of what it looks like. So all the black dots are going to be in one sphere. All these kind of like darker maroon and lighter maroon are going to be in a different sphere. I don't think the projector is like doing these like colors very well, but I swear to you, these are like different shades of yellow. I like checked like the RGB codes and the HTML viz. So this is what the space as Hemming describes it looks like. He didn't draw this out. This is another thing we can do after, but it helps you kind of get some intuition for how these kind of like points might be like laid out. And given this kind of like where they're laid out, you can kind of like reason about them. So the first thing to like reason about them is that this is the best way we'd be able to pack spheres into the space. So if you think about kind of like sphere packing, right, like you want to find the optimal way to kind of like lay them out in the space, this is the optimal way, right? Like you have all points that are a distance from 2 from each other. If it's kind of like, if 2 points are kind of like a distance of 4, they're going to have kind of like this border in the middle, which is one of those grayed out dots. If it's a distance of 1, it's going to be in the sphere, same color. It's an optimal scheme. Now, the idea is that any packing scheme of sphere in space could achieve the desired results. So this is one way that we're able to use the logic of Hamming codes in order to kind of like visualize how we might be able to kind of like, correct codes in the sphere. But you can move these dots around whichever one you want, right? Like you can swap them around, you can change the order, you can like change the, way they are. As long as you keep a packing scheme that has this kind of like center of the sphere, it's kind of like the big dot, and then you have the 8 around them, you'll have a scheme that necessarily allows you to correct a single error and detect 2 errors. Hamming takes this idea and he talks about these schemes as being systemic. So a systemic scheme is not something rigorously defined, but you can kind of like tell the difference between just like moving dots around and then having like a scheme where like the parity checks are kind of like isolated from the message themselves. And what he says is like, we can kind of like define a kind of like sphere packing bound right here, right? So if you give me like some number of n and some distance between these spheres, right? In this case, the distance between every sphere, between the center of every sphere is 1 is error, 2 is detect but not corrected, and then 3 is a single error of a different one. So the distance between all these balls is 4. This is kind of what he has in the middle here. But if you give me any kind of like distance between those spheres, I should be able to like define a packing scheme that achieves this. Like I know I can do this, I just don't know how, right? Like I don't have a way to construct a kind of like code that achieves this the same way we constructed earlier. I just know it's possible because at the end of the day, all we're doing is reasoning about kind of like spheres around these code points in this bit space. He finishes by referencing, he's like, the only previous work in the field of error correction that has appeared in print so far, the author is aware, is that of MJE Golay. My French pronunciation is awful. It's a 1-pager. I'm showing it here. This is outside the scope of this talk, but it's a really cool paper. And there are some like proofs that were done later that show that like the Hamming scheme and the Golay sphere are like the only 2 schemes that achieve like perfect codes under certain parameters. So it's kind of interesting that like almost by accident they discovered the only 2 ones that worked. There's also like really cool applications between like the Golay scheme and like group theory, but again, outside the scope for this, kind of ask me about it later. I want to kind of close out with like a little bit of thoughts here. So the thing that Hamming did, right? So in 1960, he retired from Bell Labs after being there for like 14 years, and he spent his days teaching. He retired in 1976, and he taught a course in the Naval Postgraduate School. And it resulted in a book. It's called The Art and Science of Doing Engineering. It's published by Stripe Press, which I didn't know until I like found this book that Stripe has a publication business. It's also weird because like I saw their billboards like walking over here, but I guess like publish books now too. It's kind of like that meme with a factory. Like I guess we're doing books. A lot of the stuff he says, right, like is like advice is really easy to give, and he's just kind of sitting there and he's kind of like old and kind of like dignified and talk about like doing important work and like being serious, and it's a little tired, but some of the things he repeats like have some truth to them regardless, right? Like you should work with an open door. That was a big thing at Bell Labs, right? Like always have your door open so you can have kind of people come and like ask you questions. Work hard, like have goals. He also had this is a complete non sequitur, but he has an anecdote about how to like do good work. He had to like sit with serious people, and like all the mathematicians were sitting at lunch and like doing like riddles and like playing games. So he went to go sit with the physicists who were like doing like serious work, which is ridiculous, right? I could talk to you about some of the riddles they did. Like Shannon is one of those people I think he thinks about. And he did some really cool stuff as playing games. But like the thing he does talk about in this book, and I did find really worthwhile, and I've kind of been thinking about this dude for like 3 weeks now as I've been preparing this, is the process by which he arrived at these codes, right? And you kind of like look at this construction, right? And it kind of works, and you can like demonstrate some properties about it. You can like reason about the space it creates. But it's like, how did he get there, right? And he talks about how he like thought through like parity checks and existing coding schemes. He talks about how he had the idea of like lining up the parity checks with the information bits after like being able to like carpool with like the mail car that went from like the Murray Hill offices all the way to like downtown Manhattan, and like he was sitting there and stuck in traffic and thought about kind of like distance between things. And this kind of like message, right, of like you kind of have this particular problem and you know something is possible and you kind of like reason about it like slowly and kind of like intentionally. Like I think it's cool, and I think it's not something we encourage ourselves to like do enough. The other really cool thing, and for all interested, there's a really good book, The Idea Factory, about Bell Labs. It was a fascinating time in like history, right? I think the thing that to me really stands out about this paper is the idea of like information as being kind of like binary, the idea of like, digital computing, right? Like these kind of things that like underpin the things that we do here every single day were totally new, right? Like it was 70 something years ago. And yet the way they approached the world and the technology around them was like so fundamentally different, right? And there's a lot of like assumptions that they were able to kind of like think through about how things should be structured, how things should work. They use the language of discovery a lot, right? Like when they talk about like the transistor, even when Hamming talks about their own codes that he like construct, develop, like the verb is discover, right? We discover these things. We discover transistor. We discover these codes. And I think it's really cool that like it was all done through like what was otherwise like an environment that like at its height was about getting phones to work better. Um, that's it. That's the talk. I appreciate all of you for listening. These are the sources, and ask me any questions. Here's-
Darren will have a mic. Do we have questions? I'll point at you. You'll hold it until Darren gets to you. One right here.
Did you do any research on like when the first practical application of this was and like how?
He talks about in his books, they were able to deploy it in some like relays that like routed between different calls. Like in the late 1940s is when he started to see it like deployed. And by that point, it was one of those ideas that became so ubiquitous that it's like almost like detached from the paper. It's just like a thing you do. So like if you want to like transmit some bits, you might as well like put a circuit with a bunch of XORs in there just to like check yourself to see if like something at some point went wrong. It just was common sense.
One more.
So how does modern error correcting memory work? Does it work just like this?
Literally like that.
Well,
Literally like that. It's like literally that same circuitry that I showed the schematic earlier is like what it looks like. The thing that like started happening afterwards is like people started thinking a lot more deeply about what like codes could be, right? And like how you might be able to correct different classes of errors. If you've ever used like like a like CD or like DVD disc, they use what are called Reed-Solomon codes, which use like math from like like constructing polynomials on top of kind of what do you call them?
Curves.
No, it's curves, but what's the name of the space? They're on quotient like spaces. Not elliptic curve, a little different. I can kind of like show you it works, but like there's a lot of like really cool math that was done by just like thinking about like like bits, right? Like strings of bits is like numbers and how you might be able to like use them in like different metric spaces, and like they achieve all sorts of like different properties. And this is why you can kind of like scratch through your DVD and it still kind of like works. But like the world of codes is like exploded. Like the world of like codes for quantum computing is like like getting established, and there's a lot of like really cool research, but a lot of like stuff that's still left to do. But like this was like the beginning of like developing a whole class of technologies that are like so like integrated into like everything we do every day that we kind of like don't think about them, right? We forget that like it used to be that like you have a relay like flip like a million times, it just stops flipping.
But in the end, this like his theoretical limits are still in place. Like you can't go better than he already said.
You cannot have a code that is more efficient while achieving single bit error corrections. So like that was a perfect code, right? And it's a perfect code because you have the bounds for how much information you can kind of like shove in there. I'm like feedbacking. And if you're able to like shove that much information in there, you have a perfect code. So people call this like the Hamming bound. So the kind of idea is if you define a code, you have an amount of information. If you can show that like you meet this Hamming bound, you pack as much information there as you can, achieve certain properties, it's a perfect code. But like there's other codes that are like quote unquote perfect that have been developed since, but like for single error correcting codes, like his and Goya's are like the only two that actually work, and that's like been proven.
So modern memory, it still only can fix 1-bit errors, it can't fix 2-bit errors?
It doesn't so there's different ways that people do this, right? Like generally this works when the rate of errors is like really low, right? So like you only need to fix like like if you're transmitting, let's say like a block that has like 256 bits, right? Like if the error rate is like really, really low, which it often is in like modern memory, like that's acceptable, right? It's not acceptable in other applications like storage or like RAID arrays where you need much better error correction. So you don't use semicodes, you use like Reed-Solomon codes or something else.
One back there as well. Yeah. In the pink back in the raise your hand again. Yes, yeah, I can find you. Yeah.
I guess it's about like the constant k,
Mhm.
like the number of bits that get flipped.
Mhm.
Like I'm trying to reason myself. There's actually no way to know if your code is wrong, right? Like if sufficient number of bits are incorrect, you'll never actually know that it's wrong. It's
Yeah.
not possible to know. Is that right?
Yeah, so let's think about this by thinking about the space, right? Like think about a bit flip as like walking from one point of the space to another point of the space, right? Like if you're here and you have a bit that gets flipped, you'll end up with kind of like one of these points, right? Like you'll end up knowing exactly which one of the bits kind of like got flipped. If 2 bits got flipped, you have no idea where you are, right? Like you're gonna end up in one of these kind of like discolored areas, which you can kind of like see right here. But that's kind of like why thinking about them not necessarily as like, like a bunch of XORs, but rather as like you kind of traversing the space of like binary strings is like useful, right? Because then you can say in your say like, if 1 bit got flipped, you can correct the error. If 2 bits got flipped, you're lost. If 3 bits got flipped, you're now closer to a different circle. You've like crossed from like inside of this circle into inside of like a different circle here. So like, and you run it through like, your kind of like correcting mechanism, like it won't correct back to this, it would correct back to this. But like, this is how you can like kind of think about the number of bit flips, the number of errors, and reason about where they'd kind of like put you in this kind of like sphere packing.
But there's never ever a way to like know for sure that's happened.
No, that's the point, right? Like you can still like get some amounts of errors, right? Like it doesn't guarantee you anything beyond like the parameters that are given, right? Like if 3 bits got flipped, like you don't know where you started. You don't know for a fact that 3 bits got flipped in this code.
I guess in practice, then how do you like guess what the k is?
You just have to choose it. You just like it's a choice you're making, right? If your error rate is really low, like when you have computer memory, then this scheme like makes sense because like you can, you're gonna have 1 bit flip every once in a while. If your error rate is really high, right? Like if like the size of kind of like these spheres, right? Like if you have, for example, like 10 errors and you want to be able to kind of like correct into them, this is where you want to use like different codes. And again, we don't know if these codes are going to be perfect. We don't know what's the best way to construct like a perfect code, but I can give you like a really bad code for it. I can give you a code, and that's just like going to be using like repetition. Or I have it like right here somewhere, right? Like if you want to like, for example, like, have a scheme where like you have some message and let's say it has like 12 bits and you're worried about like 10 bits getting flipped, you can just like send it like 11 times, You can just like send it a bunch of times. You can add as much redundancy as you want to achieve certain properties. It's just not going to be a very efficient code. It's not going to be perfect.
It might also be a way to say, to figure out what k is, you have to do that empirically on the wire. Right?
Exactly.
So you measure your k empirically, say, oh, I only lose 1 bit per 100,000 messages because like I know both ends. Like I send it through a bunch of times. I check on both sides. But if I lose 100,000 messages out of 1 million, I need a better code because that's a much larger k. I think k is something you find out empirically ahead of time and then pick the encoding to match your real world experience.
Cool. More questions. Great. Keep them running.
I didn't see those first. Go back.
So has anyone done this with a sliding window kind of thing? Like
What do you mean a sliding window?
if basically since you were mentioning that this was for telephones or something like that, like multiple packets are being sent continuously. So you take 8 bits of information and then you slide 1 by 1 bit one by one bit, and then you try to apply a Hamming code on that. Does that achieve more error? Like, how does that affect K? Is the question.
Interesting. So let's think about K as just like the amount of redundancy you'd have in the scheme. So like I'm just reasoning top of the doing like arithmetic on the spot is something I think we're all like pretty bad at. But like let's say you have like 4 message bits and you have like 4 kind of like correction bits, right? And then you transmit, let's say, like the first like 2 bits, then the second and the third, and the third and the fourth, right? So you basically have here is a 4-bit message, and you transmitted it by basically having like some amount of like space, and then you kind of like corrected it. So like the redundancy here would be like how many times you like resend the message times the K of the original scheme. So if you use this original scheme and then you send it 3 times, I think the K in this case would be like 12. I'd have to like sit down and like try to like prove it to myself, but like this is my intuition, right? Because like K in this case like just describes the amount of like redundancy you're adding. How this would like translate into like the size of the sphere and how many errors you have to correct, I don't know. I'd have to think about that.
And a question, this one pass the mic over there.
Seems like the work he was making, he was doing, was assuming that the stability of the error correction bits is the same as the stability of the rest of the bits. Right? In other words, the chance that the error correction bit itself.
So this scheme, this is what's really cool about it, because you're just XORing all of the various positions. Like you could have a flip in the parity bit just as much as you can have a bit in the message bit. It wouldn't make a difference, yeah.
My question is whether there's work that uses 2 mediums, right? One is more stable but way more costly, and the rest of the information is cheap. Whether you can achieve better results.
I have no idea. That's really interesting, but I have no idea. Like if you have kind of like 2 wires running next to each other, and one is like kind of like a thick cheap wire, and another one is like better. Yeah, yeah.
So you don't have to worry about the collection.
I have no idea. That's a cool idea, but I have no idea if it was done. If anybody does know, like please, raise your hand or like sound off. But I can tell you.
Well, I'm just thinking about other applications that we
Yeah.
typically have, not for correction, but for tampering, right? So we have the shock. So
Mhm.
it's on the side. We use that to check.
Oh, so what you're doing is you basically almost like using like a physical checksum almost, right? With like the different medium. Yeah, I mean, I gotta think about that. That's cool, but like I'm way out of like my my kind of like depth. Like
It's a different problem space. But
yeah.
You could probably model it as, you said one wire is more expensive than the other in a way. You could model that as X the redundancy on a fatter pipe. Think about it as if you unify the bandwidth there somehow. Send 10 parity bits or something like that. It would probably model something like that. I'm not a computer scientist, but I feel like you would model it as a unified object with more overhead. You model that merge out. You may have a smart thought on that.
Yeah, and you model it.
Give me pass.
All this drops down to Shannon entropy and the expectation of loss of information in the channel. And so if you have 2 channels and you model them separately, you have to treat your effective noise rate separately, and you would end up coming to your own error correcting code that prioritizes your low noise channel.
Do people here know what Shannon entropy is, like broadly? Like, is that like a term that like people are kind of like familiar with a little bit? So like, think of it again, like there's ways to like make it mathematically like rigorous, right? But like think of it as like how surprised are you that you got something you didn't expect, right? Like we got an error, that's kind of like surprising. We wanted like a valid code, like something happened there, right? Like you think about the entropy about kind of like all the different ways you can kind of like be surprised, right? So if you have like this medium, right, that like we know empirically has a lower error rate, like we know it's probably going to have a lower entropy because it's going to like surprise us less than like maybe like the coarser medium. This is like a super over the top, like not exact, not rigorous definition of it, but maybe this is kind of like how you can think about it. Yeah. Yeah. I'll be here if you want to ask any questions and you want to come play on my computer. I have this on localhost, but this will be on a website available from the public internet in the next few days, and we'll send it out. But thank you all for listening. Again, really appreciate people coming out and engaging with this. And stay tuned for the next Papers We Love.
Yeah, join the Discord. The links will be there. Links to the slides will be there. We'll have a video up in a month or so. And printers, what's it called?
Printer's Alley.
Printer's Alley. Printer's Alley. Put it in your phone. Printer's Alley. 7 and 8.
Keep the minutes up.